This conference will now be recorded.
Okay, so let me just say it again rather quickly. The subject of random matrices that we will deal with is indeed constituted from these basic ensembles of random objects, which are n by n matrices, where the entries mjk's are random variables, which might be either real or complex. And the basic questions that we are after concern the statistics of the eigenvalues or the eigenvectors of M. Maybe just one question. Can you see properly the board? Because I have the feeling that it's a bit hard to read.
It's okay.
Yes, it's good for me.
Okay, fine. Very good. So as you can see, of course, this is a quite general setup. And as I said, it turns out that these questions have found a lot of applications. And in physics, these random matrices were actually initially introduced in the context of nuclear physics. By Eugene Vignor in the 50s. And the idea there was that people wanted to have an idea of the energy levels of a complex and big nucleus. And instead of solving the full Schrödinger equation, which would be extremely complicated, even numerically, people started to argue that in some cases, one could approximate the spectrum of such heavy nuclei by the spectrum of some random matrices. And that's how it started in physics. And it had afterwards had a lot of success, not only in nuclear physics, but much beyond in many different areas of physics. And you could consult this Oxford Handbook of Random Matrices, which were edited a few years ago. Many chapters are actually free that you could find on the archive. And we'll just, I will not be exhaustive, of course, but let me just mention some topics which are related to the subject of this course. One of them is the subject of the quantum particle in a disordered potential. Okay, so typically you could ask, look at a very simple problem where you would look at such a Hamiltonian here, but where the V there is, because of the presence of impurities, is a random function which typically would have this kind of shape here. So that's sort of related to some problems that we have studied. Now, in general, what you have so that means that in this case, H hat is a random operator, simply because V itself is random. And if you, for instance, want to study this problem numerically, then you would have to say discretize this random operator, and that would naturally lead to a random matrix. Okay, so that's after discretization. And you would like to say something about the spectrum of H. You would like to say something about the eigenvectors of H. And this has to do with the problem of localization that we will study next week. But you see indeed that random matrices naturally arise in this context. Now, other topics that we could think of would be, for instance, the subject of quantum scattering in disordered media. Maybe you have heard a bit about it in the lecture by Christophe Texier and Cheroret. Again, in the context of disordered systems, I just mentioned it briefly during the last lectures. But in these ordered systems, for instance, if you look at directed polymers, as we did last time in random media, well, they turn out to be related to random matrix problems. Maybe I will say more at the end of this lecture if I have time. Another topic that we have already encountered, and which is of course directly related to random matrices, is the problem of random graph. Right. So if you take, say, a graph J, which is just given by the set of vertices and some edges, well, you have seen that a natural way to encode the properties of this random graph is to look at the adjacency matrix. Now, it's clear that if you have a random graph, then clearly this adjacency matrix would be random, okay? And that means that studying the structure of this random graph to a large extent amounts to study the spectral properties of this random adjacency matrix. So the list is extremely long, and it's clear that I will not have time to cover all these topics, but just to mention a few topics which touch upon different domains of, say, mathematics and probability. One is turns out to be related to the number theory. It turns out that the properties of some random matrix ensembles are actually connected to the zeros of the Riemann zeta function. I will not say much here, but I could provide you some references if you want. There are also very nice problems of combinatorics, which are related to random matrix problems. One famous problem is the so-called longest increasing subsequence of random permutation. Longest increasing subsequence of random permutations, and so on and so forth. And this is just to tell you that somehow these random matrix problems are the interface of many different topics, at the interface, say, between statistical physics, mathematical physics, probability, combinatorics, graph theory, and so on and so forth. And as such, they are widely studied, and they constitute a very, quite active subject of studies nowadays. Now, it turns out that I mentioned Vignor in the 50s, but it turns out that, and I will just end up with that, it turns out that the first application of RMT, as far as I know, and as far as usually people refers to it, the first application was actually in statistics. In the late 20s by John Wishart. Actually, he has a famous paper from 28, where the topic was the following. He was kind of interested in some correlation matrices when analyzing, typically doing some data analysis. So what he had in mind was to look at some, say, a vector, which is labeled by T, which might represent time. So you might think of T as a discrete time, and X is a vector with, say, capital N entries. So what these entries might be, so I just denote them by X1T, X2T, XNT. So for instance, this might be the temperature on the day I in some city, in some given city. This might be the price of a stock option if you are just considering a kind of portfolio here. So this might be various entries. So you might think of it as a kind of time series where you might have again the price of stock one, or that might be the temperature on day one, etc. And what you are interested in is to study the correlations between these different entries. Okay, and to do that, the object that you will consider is what I will denote by C hat, say GK, which will be constructed in this way. So that will be 1 over T times the sum from T equal 1 to capital T. So you observe your data on a set, say on an interval of duration capital T, and you just look at the correlation, which you would define this way: xjt, xj comma t, xk comma t. Okay. So that's a correlation matrix, and typically because these guys here, these objects here are random, this is a random correlation matrix. And again, in order to get some information about these correlations, it turns out to be very useful to look at the spectral properties of this matrix. Okay, and that's roughly speaking that's the aim of principal component analysis, which you might have heard of. And generally speaking, this kind of models, then this kind of random matrix models play a very important role in data analysis, and in particular in finance. So maybe if some of you are following the lectures by Jean-Philippe Bouchot, probably he has been discussing a bit this kind of correlation matrices. So that's a very brief overview of the applications of random matrices, and I just would like to discuss with you a kind of prototypical ensembles of random matrices which are relevant for us, because as it is here, of course, you see it's very general. I didn't say so much about the kind of matrices that I want to study, and depending on the problem at hand, we will have to face different kinds of models. But I want to study and to discuss with you one of the most general ensembles that have been introduced and discussed. And for this, I will essentially follow Vignor and discuss what are called the Vignor ensembles of random matrices and the Gaussian ensembles of random matrices. Okay, so that's that will be the second part, which will deal with ensembles of random matrices. Okay, so let me be a bit more precise about the kind of models which are interesting. And of course, and that's also the reason why they are interesting, we will see also that they carry some universality. There is indeed some universality behavior, some universal behavior that emerges when you look at large matrices, and that's why they are interesting, of course. Ensembles of random matrices. So I will follow again Vignor, and I will restrict myself to the cases where the matrices M have actually a real spectrum. Okay, so that means that I will specify, we consider here matrices whose eigenvalues are real. Okay, so again, following Vignor, that was kind of natural because he had in mind that these eigenvalues might be the eigenvalues of Schrödinger operator, which is Hermitian, and therefore the eigenvalues have to be real. So that's why I will stick to this case here, and that means that I will consider the case where M, the matrix M, is either real symmetric, okay, or complex Hermitian. So these are the two main ensembles that I will have in mind during these lectures. And it's clear that in both cases, of course, the spectrum is purely real. Now, it turns out that if you restrict yourself to that, it turns out that there are two main natural ensembles that can be introduced, and that's what we are going to see. Okay, so there are two main types of ensembles, two main categories of random matrices. I'm not saying that these are the only one, but some are the most interesting one for practical purposes. The first one, and this is the one that was introduced by Vignor. This is the ensemble that I would like to call ensembles with independent entries. Okay, and this is what we call usually Vignor matrices. This is what is known under the name of Vignor matrices in the literature. So let's be a little bit more precise. So in principle, since I want to cover both cases here at the moment, I may have both a real part and an imaginary part. Okay, and these guys, of course, are real. Now, in this set of ensemble, you give a probability measure on the set of random matrices by simply saying that, okay, let me just denote, if you want, the PDF of M. That's just the law, if you want, of all these matrices, these matrix elements. Now, of course, I want them to be either real symmetric or complex Hermitian. So that means that the matrices have a special symmetry. And essentially, if you look at your matrix M, what this says in both cases is that you need to specify, say, the entries which are both on the diagonal and on the upper triangular part of the matrices, and then this one here is fixed by symmetry. Okay, so that means that you fix this one, you give this one, and the one here, they are just fixed by symmetry. Okay, so in other words, the way you will just so how does it look like? Well, the probability. So what will be the joint law of these guys? But of course, let's first look at what happens on the diagonal. Well, on the diagonal, they all need to be real. So actually, YII is just 0. So you give, you provide such, let me call it Fi for XII. So I give you some law for these guys. Note that they might be different. And then I will just specify the law of both x and y on this upper triangular part. Okay, so that's something which I will simply write this way. So that will be a product for j less than k, f of jk, first of this guy, x, so real part. So let me call it r, and then f of I for imaginary, jk of yjk. Again, in principle, these distributions here might depend on j and k, so that means that you will have a set of independent entries, and this you see because the joint law of the entries is just a product, but they might be that they are not necessarily identically distributed. Okay. Just one remark here that would be useful in the following is just to count how many independent degrees of freedom do you have in such a matrix, and that's actually let's consider the case of real matrix, because you can just do the same counting for Hermitian, but for real symmetric matrices, so the number of independent degrees of freedom well, it's relatively easy to count, right? Because you can just, again, I say that the only independent degrees of freedom are the entries which are on this upper triangular part. So on this line here, I would have one guy, then here I would have two guys, and here I would have three of them, etc., etc. Okay, so this is just 1 plus 2 plus 3 plus this last guy here, where eventually I will have n entries. Okay, so that's just n plus 1 by 2. I will come to that later on. And you can do a similar counting argument, of course, for complex Hermitian with a different answer, but the same reasoning. So these are the Vignor matrices. Okay, so that means that you really think in terms of how you feel the matrices and what kind of matrix elements you have. Now, there is another way of, and that will be the second category. There is another way of giving a probability measure, providing a probability measure on these random matrices, which is more related to some kind of symmetry considerations. And instead of Vignor type of matrices, Vignor ensemble that I first study, I would like to introduce the rotationally invariant ensembles. So there is a notion of symmetry there, which is slightly different both in the case of real symmetric and complex Hermitian, but let's illustrate it on the case of real symmetric, and you will see immediately how it generalizes to the second case. Okay, so that's the second ensemble, that second category, which I would call rotationally invariant, which are called rotationally invariant ensembles. So here is the argument, or say the motivation. Let's suppose that that M is symmetric, real symmetric. So in this case, I can diagonalize this matrix, and I can diagonalize it by an orthogonal transformation. So that means that there exists a set of matrices, which I will denote by O and lambda, such that O transpose is just equal to 1, or say identity, and such that M is just O lambda O transpose, or O minus 1 if you prefer, it's the same. And lambda here is just where lambda is just the diagonal matrices with the eigenvalues of the matrix M. Okay, so these are my entities. Lambda 1, lambda 2, lambda n are the eigenvalues. Okay, so the idea of this second class of ensemble is basically to say that if you are mainly interested in the eigenvalues of your system, and if you are mainly interested in the spectral properties of your matrix, this is somehow quite natural to define a probability measure which is invariant under these rotations. In other words, you can try to find this probability P of M. So you will say that P of M, which is the probability measure on the ensemble of such random matrices, P of M is rotationally invariant if and only if basically P of M is just the same as the distribution of P, but with the sum for all matrix O such that O transpose is equal to identity. Okay, so that's what we mean by rotationally invariant ensembles. Now you see, and we will be a little bit more precise in a minute, but it's relatively easy to see that in such ensembles, the eigenvalues in general will have a non-trivial statistics, but the eigenvectors somehow are a bit more trivial in the sense that because of these properties, you can already guess that the eigenvectors actually are just uniformly distributed, and there is no special structure for the probability law of these eigenvectors. So the main interest in this case will be on the eigenvalues. But you see that in general, this defines two big classes, and it turns out that these two big classes have actually found a huge spectrum of applications. Now, natural question is to ask what is the intersection of these two ensembles? Okay, is there first is it non-zero? Is there any intersection non-trivial matrices which belong both to A and B? And if yes, I mean, if it's not empty, how these matrices look like? It turns out that the answer to that question is very simple, and this is known under the name of the what is called under the name of the Porter-Rosenzweig theorem. So let me spell it correctly. Which is a theorem from the 60s, and which answers that question and says that the only ensembles, so the only matrices, the only P of M that satisfy A and B, that are both that I can see as a distribution with where the matrix elements are independent random variables, and which is also symmetric, rotationally invariant, is the case where P of M is a Gaussian. Okay, so more precisely, of the form P of M is just equal to, say, up to some normalization, exponential of minus alpha trace of M squared minus beta, alpha, say alpha 1, minus alpha 2 trace of M for alpha 1 and alpha 2 positive. Well, alpha 1 positive, sorry. And alpha 2 real. Okay. So this is, of course, a non-trivial statement, but let me just remark or see why this P of M actually do belong both to A and B. This should be clear that this is actually P of M naturally belongs to that case, right? Because the trace is invariant under rotations, okay? So it's clear that P of M belongs to B. Now, how is it that, how can I see that P of M belongs to A? Well, this requires a little computation that I want to do here because it's not completely trivial, I think, to see that. But let's see how it works. So this is the this P of M. So this is just a remark or say check. Well, the first one is clear, so I will not. So P of M belongs to B, or is rotationally invariant. Or say satisfies the property B. Well, I think this is okay, so I will not give more details here. If you want, I can elaborate more. But now that P of M satisfies A is less clear. So just to, yeah, let's do it both with both alpha 1 and alpha 2. Well, the idea is relatively simple. Is that if you look at P of M, okay, there is a 1 over Zn. So let's write what it says. So the first term is easy, right? So this is just minus alpha 2 sum from I equal to 1 MII. This is just the trace. And this is quite clear. This is simple. And let's look at the other one. So the other one would read this way, okay? So that's the sum over ij. In principle, this is mij, mji. Okay? Now this mji here is just mij. Okay, so okay, let's do it this way. So I will just separate. So maybe this guy, I mean, I can just do it easily because this one, you see, this one is simple, right? Because this one is just product of that form. So that's easy, okay? So that's indeed of that kind. Now, what about this term here? Well, again, this term, I will just disentangle the diagonal terms, I equal to j, and j not equal to I. So I'll have a first term which will be of that type, from I equal 1 to n of mii squared, which is fine because it's again of the same kind here, but with a square. So that's of this type. And then the other one will be of that form. Will be the sum from I not equal to j of mij times mji, but I can now just use this property here that tells me that mgi is equal to mij for I not equal to j. So that's actually just a square. Okay. And now this is essentially done because this, you see, you can again this sum here, I could again write it as exponential of minus alpha 2 and just restrict the sum here to I less than j, but then I will pay a factor of 2, so I will have 2 alpha 2 sum from I less than j mij squared. Okay, so at the end of the day, if you rewrite everything, you see the following, that indeed okay, well, I think we have understood how this should work. But P of M is just 1 over Zn. So I have this product from I equal 1 to n of alpha 1 alpha I squared minus alpha 2 MII. And then I have a product from I less than j of exponential of minus 2 alpha 1 Mij squared. So there is actually so that says that indeed this satisfies A. Okay, so P of M is indeed A. But you see that this is really due to the Gaussian, right? That means that it's really due to that specific properties of the Gaussian, but that satisfies A indeed. Now there is more here. There is more to say. In fact, if you set alpha 2 equal to 0, well, then you see that both the diagonal and the off-diagonal terms are centered Gaussian random variables, but with a variance which is twice on the diagonal compared to what it is on the off-diagonal terms because of this factor of 2 here. Okay, so there is a subtlety here that even in this case, both the diagonal and the off-diagonal terms are slightly differently distributed. Now, of course, because these Gaussian ensembles, so that's a kind, it's the generalization of the Gaussian, if you want, but on the set of random matrices. Okay, so that's a nice and simple distribution. And the fact that it is at the intersection between A and B, so these are both Vignor matrices with independent entries and rotationally invariant, of course, that gives them a special interest because of this Porter-Rosenzweig theorem. And these ensembles actually are probably the most well-studied ensembles. And in the real case, so for alpha 2 equal to 0, this is what we call the Gaussian orthogonal ensemble. Okay, so that's a very well-known instance of random matrices, and I will just be a bit more precise then. And that in the following, we will mainly focus on this ensemble, which are both Vignor and rotationally invariant matrices, and we will stick to this ensemble. Okay. So in the following, we will study this ensemble, this Gaussian ensemble, and in fact, I will, on top of that, I will set alpha 2, sorry, alpha 2 equal to 0. Okay, so these are this corresponds to the case where you have Gaussian centered random variables. So that means that all the entries are 0 mean. And in the case of real matrices, this is what is called. So in the case for M real, this is called the Gaussian orthogonal ensemble. Maybe you have heard already about this ensemble. This is usually called GOE. So while ensemble is clear, Gaussian is also clear. Orthogonal should also be clear because of this invariance here under orthogonal transformation. I mainly discussed here the case of real symmetric, but this can actually be generalized to the case of Hermitian complex Hermitian matrices, and in this case, you have also the equivalent of the Porter-Rosenzweig theorem, which tells you that in this case, so if it's real and symmetric, of course, and here it's complex Hermitian. And this is called, in this case, the Gaussian Unitary Ensemble. Which is called the GUE. It's also very famous. And unitary, because in this case, of course, in this case, when you diagonalize your Hermitian matrices, then the matrix that you have is not an orthogonal matrix, but it's a unitary matrix. Okay, so instead of having the transpose, you have the transconjugate. Okay. So these are the two main ensembles that I will discuss, and in fact, most of the things that we will compute also during the tutorial will be for the GOE. Are there any questions? Okay. So now the point is that we have this Gaussian measure. This is a measure on the matrix, on the random matrices. And of course, what you would like to have is to get some information on the spectral properties of M. And typically, what you would like to compute is the distribution of the eigenvalues and maybe of the eigenvectors. Although we already said that the eigenvectors are probably trivial here. But that's what we are after. Okay, so we really want to compute the joint distribution of the eigenvalues of these matrices given this Gaussian weight. So there are various ways of doing that. I will present one method here. I will not do the full computation because it's a little bit tedious, but I will just give the main ideas. And in fact, next week in the tutorial, we will find another very nice way to get this distribution using what is called the Dyson's Brownian motion that we will see next time. But today we will stick to the there won't be any dynamics here, no Brownian dynamics, just purely statics. And what we would like to compute is the joint law of the eigenvalues, say for GOE and GUE. Okay, so let's stick to the to GOE, and at the end, I will just show you what are the modifications that you would expect. Okay, so that means that M is just equal to M transpose, and it has a diagonal form, which is quite convenient, of course, and that I will write under this form. Okay, so lambda is just lambda 1, lambda n, okay, and O transpose is just the identity. And these matrices actually have of size n by n, okay, so that's identity of size n here. And I have n eigenvalues. Now, again, because the entries of M are random, you would expect that the lambda i's to be random also, okay? And you would like to compute the joint distribution of these lambda i's. So what's the trick, and how do you do that? Well, first let's come back to the number of independent degrees of freedom that I did before. You see, I had this matrix M. You remember that it is like that. So it has this upper triangular form here, and then this one is fixed by symmetry. Okay, it's fixed simply because M has to be symmetric. So the number of independent, again, the number of degrees of freedom, independent degrees of freedom, Okay, I mean, we have already computed it. This is just n plus 1 by 2. Okay, so we counted the number of entries which are independent on this matrix. But what it says when you write the things like that is that there are essentially two different ways of parameterizing your matrix M, either via this n plus 1 by 2 entries, or by the eigenvalues and the set of eigenvectors. So in other words, it's quite natural to write this total number of degrees of freedom here. I just can again write it as n, which would be the total number of eigenvalues, plus what is left, and which counts exactly the number of degrees of freedom that are left in this orthogonal matrix. And it's quite easy to see that this is just n minus 1 by 2. Okay, you can just identify that. Now, what I want to mean by that, or to say, is that I have initially the probability measure is really given on the sets of the entries, and I would like instead to compute the probability measure that it does produce on the matrix O together with the eigenvalues lambda. So what I will do is, what I want to see is that there is a kind of natural change of variable, if you want, which goes from M, essentially, to these couples lambda and O. And that's essentially the same kind of things, up to some permutations. But and what you really want to do is that you know the P of M, Mij, okay? So this is given, and simply given by that. And what you would like to compute is the P of the lambda 1, lambda 2, lambda n, and the matrix O. So that's really what you are after. Okay. So when you have such a thing to do, if of course here it's slightly more complicated because it seems that there is a huge number of variables, but think if you just think about of reduced values of n equals 2, for instance, n equals to 3. Well, basically, you really need to compute this change of variables, and the only effect that will happen when you do this, I mean, to go from that guy to this other guy, is simply to compute the Jacobian of this transformation. Okay. So in other words, what I want to say is that I can write quite formally this joint law that should be simply equal to P of the Mij times the Jacobian of the transformation. Okay, so let me write it this way. That will be simply some determinant of J. And what is J? Well, J is a relatively complicated matrix, but that's just the Jacobian. Okay, so J is the Jacobian of the transformation. So it's a complicated matrix, but formally it's easy to write, right? This is just a matrix whose entries I'm not writing it explicitly, but this is simply something like that, right? You just need to compute d of Mij divided by d of lambda k, and d of Mij divided by d of OKL, say. So it's a beast, right? I mean, it's a complicated object, and computing these things here, of course, can be done in principle only starting from that together with that. This is the only thing that you know about this this matrix O and lambda with respect to M. Well, it turns out that after a quite tedious computation, the result is extremely simple. So this is something that you can find in some textbook, in various textbooks that I could give you some reference to that. But the final result is deceptively simple. But this requires quite some manipulations which are not completely obvious or simple, but it's just calculus, right? There is no real trick, at least if you do this way. But what you will find is that this determinant of J, so after some tedious calculation, I insist on that because, okay, I will not do that. So I don't want you to believe that this is just straightforward, but some tedious computations. So again, in the case of GOE, what we find that the determinant of J turns out to be extremely simple, which is simply the product from I less than J of absolute value of lambda I minus lambda J. Okay, so that's quite remarkable. And what you also see is that this is independent of O, independently of the matrix O, which you could have anticipated because, as I said, because of this rotational invariance, we see or we know already that the eigenvectors do not play a very important role, and somehow it says that the eigenvectors are just uniformly distributed, and that's what it says. Okay, it means that the distribution of the lambda i's and O do not depend explicitly on the eigenvectors. So that's for that guy. Okay, and well, this guy you see is relatively simple to compute because we have said what we said, that we wrote we looked at the GOE ensemble, okay, and what we had is that this was proportional to exponential of minus, say, what I called alpha 1, trace of m squared, okay? But trace of m squared is very simply expressed in terms of the lambda i's, okay? Because this is just the sum from I equal 1 to n of lambda I squared, okay? So now, if I just use this and that result for the Jacobian inside this quantity here, well, at the end of the day, I obtain a quite simple expression. Let's write it explicitly. And eventually for GOE, what we find is that the joint distribution of the eigenvalues and the eigenvectors O is up to some constant here. Normalization constant is simply of that form: alpha 1 sum from I equal 1 to n of lambda I squared times the product for j bigger than k, lambda j. Okay, so that's the answer. Now you see it's independent of O, so I can immediately get the marginal distribution of the eigenvalues by integrating of O over O. So that will give me some additional constant, but at the end, you can just get also immediately the marginals of P of lambda 1, lambda 2, lambda n, which will be, so I will have a modified Z tilde here, but then I will just get the same kind of things. So let me just write it in this way. Exponential of sum alpha 1. Okay, so that's a very nice expression here. It's quite simple, and this was actually derived by Vignor and Dyson already quite some time ago. What is nice is that if you don't have this term, if you didn't have that term here, that would just be a set of independent IID random variables, simply Gaussian. But of course, you have this term here, and that term you see says that the distribution actually vanishes when two eigenvalues are exactly at the same place. Okay, so that means that in these systems, it turns out that the eigenvalues actually they don't like to be too close to each other. Okay, so there is a phenomenon which is called level repulsion, which says that indeed that two eigenvalues don't want to be too close from each other. In a way, they do behave a bit like fermions. Okay, and in fact, the analogy goes beyond this simple thing here. But somehow, you should think about these eigenvalues as fermions. That's a quite good analogy.
I'm sorry.
Now, another remark. Oh yes, please.
What happened to the alpha 2 term?
Oh yes, alpha 2. I just put it equal to 0. I just put it equal to 0 from the beginning. In fact. Is that okay?
Yes, thank you.
Okay, so if you had some alpha 2, well, it would be you would have something additional here. In fact, I just didn't want to have it, but that would just produce this additional term here. Okay, now it turns out that the GOE usually is defined without this term. Okay, so that's why I just ignored it at the moment, but it can be reintroduced if needed. Okay. Fine. Another thing that I would like to mention here is that it's a kind of observation. I will not do anything with that at the moment, but if you remember a little bit of linear algebra, this is just the absolute value of a determinant, and this is called the van der Monde determinant. Okay, so it turns out that these matrices, so this term here can be rewritten as the determinant of some matrix, which has a very nice and simple structure, and this is called a van der Monde. I will not comment too much on that because I will not do anything with that in the following. So this is for GOE. Now you could ask what happens for GUE. Well, for GUE, the things will be slightly different because, as you could expect, the Jacobian will be a bit different. And in fact, that's true. It is different, but only slightly different. And the answer for GUE, let me write it maybe. Is that instead of having the van der Monde, or say instead of having the product of absolute value of lambda j minus lambda k, this actually comes to a higher power. Okay, so GUE has also a very nice expression. So this is now okay. You have another. This is another constant, of course, but now you would get something like that. And instead of having to the power 1, you have to the power 2 here. And this is just the same. So it's very similar. You again have a level repulsion effect. Okay, some are stronger here, beta equals 2. So you have, okay, the square here. But they of course share some common properties, but we will discuss a bit more later what are different in the two cases. So again, GOE here, where you just have the absolute value. Here you have the absolute value squared, and I didn't say so much about this value of alpha 1 here. So in fact, in the literature, they are defined in such in a kind of uniform way. So usually A1 is chosen in such a way that the weights are written this way. We choose alpha 1 such that, so it turns out that we choose alpha 1 in a different way for both GOE and GUE, but okay, so let me write it this way. So I will have, okay, I will introduce some number beta here, and maybe let's stick to my notes. I will come to that, and then I will denote by minus beta n to the 4 sum of 1 lambda I squared. So I will tell you what beta is. You will get it now. And I have this Vandermonde here to the power lambda I minus lambda j to the power beta. And beta, as you can imagine or read, beta is equal to 1 for the GOE, so that's the standard nomenclature, and beta equals 2 for GUE. Okay. So that's what this corresponds to. So I have included the n here. We will see why in a minute. And I have also included beta there. We will also see why in a while. Is that clear? Are there questions? Okay. So at the moment, things are pretty much mathematical, I would say. Now, it turns out that this probability weight here has a very nice interpretation in terms of statistical mechanics. It can be interpreted as a Boltzmann weight for a kind of set of particles, and it turns out that this is related to the Coulomb gas that I want to discuss now, because it's a very nice and very useful way of thinking about random matrices. I mentioned the fermions, but before fermions, it's nice to think about it in terms of the Coulomb gas, and that's what I want to discuss. And that was actually proposed by Dyson already quite some time back in the 60s. The same Dyson had the Schwinger-Dyson equations. And this is a very nice interpretation, which is based on a simple observation, but from which one can actually get a lot of insights. So that's what I want to discuss in this third part, which is the Coulomb gas approach. Okay, so what's the idea? Well, the idea is that I want to interpret this term here, or this expression here, as a Boltzmann factor for some statistical physics model. And of course, if I want to do that, that means that I have it has to be written as the exponential of minus some energy. Okay, so this one has already a nice form. It's already exponential of minus beta times something, and you see that beta is already a little bit, plays already a bit the role of an inverse temperature. It's a bit formal at this stage, of course. But this guy, I need to exponentiate it. Okay, so the trick. So again, this is due to Freeman-Dyson. 62. He has actually a set of several papers on that, and the trick is just to write these things like that, and you will also immediately see why I wrote this beta. But well, I can just write it this way. No, this is just exponential of beta by 2 sum from I different from j times the log of absolute value of lambda I minus lambda j. Okay, I didn't do so much here. There is just a factor half here because it's slightly more convenient to sum here for all I and j's, with I not equal to j, of course. And while here I just have this inequality. Okay, so that's the only difference. But apart from that, this is just a trivial identity. Now, what is nice is that you see that I can rewrite this rate here in a very nice way. I mean, very appealing way, at least for us statistical physicists, which is that I can rewrite this way as, okay, I have a normalization factor that I don't want to discuss so much. But then I can write the things like this as exponential of minus beta. So I have my beta in factor of every one here times some energy functional, which depends on the lambda i's. Okay. Now, what is E? Well, E, you see, what I call E, or the energy, I have two parts, two components. One first component, which is simply this confining term here. So that's n by 4 times the sum from I equal 1 to n of lambda I squared. And now I have another part. So there is a minus here, a plus there. So I need to have a minus half sum from I not equal to j of log of lambda I minus lambda j. So that's sort of nice because I can now interpret this energy here as the energy associated to a configuration of a particle systems where the lambda i's are now the positions of particles on a line. So it's a one-dimensional system. Okay, so you have your line here. So these are the lambdas, if you want. There is 0 here. Now, what happens to these particles? Well, they feel actually two different, or competing interactions in some way. So first, there is a confining potential. Okay, so that means that all these particles, they actually lie. So there is a quadratic potential. Okay, so it's a kind of V of lambda, if you want, which is n by 4. You will see why there is an n here. I will come to that. So you have your particles, and they experience. So these are the lambda i's. Okay. This is some lambda I. So this is the confining potential, and this confining potential, you see, in order to minimize the energy, it enforces. It would be better for the particles to be all at the center of the trap. Okay. But on the other hand, because of level repulsion, there is an effective logarithmic interaction here, which is a repulsive interaction. Okay. So that means that it's like these particles, they have actually they bear a charge, so they are all, say, all of the same sign, all positive or all negative, and they interact via the Coulomb potential in 2 dimensions. Okay, if you solve the Coulomb potential in 2 dimensions, I mean in 3D you would find the 1/r term that you know, but in 2D this is the log. This is the log that we found in the XY model, for instance, and this is the case here. So that means that you have these lambda i's. In fact, they are particles, but they are charged particles. And these charged particles, you see, they repel each other via this logarithmic potential. Okay. So at the end of the day, you see, you have transformed a problem which was quite mathematical initially in a problem which is a statistical mechanics problem where you are dealing with particles on a line which do feel a quadratic potential, and on top of that, which are interacting repulsively via this logarithmic potential. Okay, and because of this 2D Coulomb potential, this is called a Coulomb gas. Sometimes this is also called the log gas, I should say. For some obvious reason. So that's what you are. That's what you need to study. Okay. Now there is another observation which somehow connects to what we have, or what you have seen during these lectures, is that you see, I mean, in this model, actually, all the particles interact with all the other particles. Okay, so it's a kind of mean field model, in the sense that you have a very long range interactions. Okay, it's a fully connected model in some sense. Though of course the lambda i's here are continuous variables. Okay, don't have spins. So what can I learn? What can I learn from that? Well, the first thing, as I said, is that there is this competition between this confining potential, which would attract all the particles in the center of the trap. But on the other hand, because of this logarithmic repulsion, we know that they cannot be as close as they would wish. Okay, so there will be a kind of competition between these two interactions. I mean, these two components of the energy, and this will lead to the fact that the energy, sorry, the density of particles actually have a finite support. Okay, so again, if there were only the attractive the quadratic potential, the density would be a simple delta function, right? All the particles in the center, if I'm looking at the ground state. On the other hand, if I had only this logarithmic term, then all the particles would be as far as possible. Now, if you consider both, it turns out that there is a kind of compromise which the particles have to find. And this compromise is that the density has a finite support and is given by the Vignor semicircle law, which we will see in a minute. So the first thing that we want to understand is what the typical extent of the density profile. So in other words, we would like to understand what is the typical value of the lambda i's in this term. And this can be estimated by balancing these two contributions. Okay, so let's do this argument, because this is something which is both hand-waving but also very useful. And that will allow to guess or to get the typical scale of lambda i's. Okay, so is it, and that will help us to understand why we put this factor of n in front of this lambda I squared. So let's try to estimate the potential energy, say the energy due to the quadratic potential. Well, let's try to estimate the typical scale of lambda I. So I will assume that all the lambda i's typically have the same scale. So I want to understand how it scales with n. Okay. Is it proportional to square root of n? Is it proportional to a constant? So n to the power 0, whatever. And I will assume that all of them typically have the same scale. And I will call this scale lambda tip. Okay, so let me just estimate separately the potential energy and the interactions. So potential energy is just simple to estimate, right? Because this is just n by 4 times the sum from I equals 1 to n of lambda I squared. So again, I will assume that each of the lambda i's is typically given by lambda typic. So I will have n by 4 times, so each of them is given by lambda tip squared. And I have n terms in this sum here, okay? So that's n again. So that's n squared, lambda squared, divided by 4. Okay, and now I want to estimate or compare this with the interaction terms. So the interaction is a bit peculiar because of the log. And if I do only kind of so let's do it this way. So this will be, the interaction will be simply minus half sum from I not equal to j of the log of lambda I minus lambda j. Okay. Now the log here, so okay, lambda I minus lambda j is typically over the lambda typic, maybe even smaller as we will see, but it doesn't matter so much because I will take the log of this number here, and the log of this number will be a number. Okay, so that means that this guy here, no matter what this lambda I and lambda j's are, this is roughly of order 1. Now, how many terms do I have? Well, as I said, this is a mean field model, okay? So how many terms do I have? I will have minus half. Okay, so let me just put half here, just balancing the two. So that will be n minus 1 by 2. Okay, which says that for large n, can just get rid of this term here, and that's roughly n squared by 4. Okay, so that's the typical scale of the energy, and it also scales like n squared. So what you see is that if you balance these two terms, well, what you find is that the typical scale lambda tip here, is typically of order 1. Okay, so that means that balancing the two. So if you again say that, or assume the two contribution, so you see here, I am actually doing a purely energetic computation. I am actually forgetting completely about the entropy. I will not comment too much on that. It turns out that at leading order for large n, this is correct. But I'm just looking at what happens if I look at the energy of the system. Okay, so it's a little bit like the kind of arguments that I was doing last time for zero, zero temperature fixed point, if you want. So if I balance the two contributions, what I will get is that I will have n squared by 4 lambda typic squared should be of the same order as n squared by 4, and that gives me that lambda typic is of order 1. This is obviously a very rough and hand-waving argument, but that actually turns out to be to give the correct estimate, and this is a very standard argument that one uses in this kind of context. So it says that, and that's the reason why I put an n there upstairs. This.
Excuse me, I believe you wanted to write O of 1, not O of n.
Oh yeah, okay. So I just put O of n to the power 0. So this is
okay. Sorry,
this
it's
is O
just
of 1.
very
Okay, I just wanted
slightly
to
visible. Thank you.
insist on that. Okay, thank you. Is that clear now?
Yes, thank you.
Okay. So that says that what you would expect from that argument is that the density, if it has a finite support, which will be the case, the typical scale of the support should be of order 1. So how can I quantify that and go beyond this thing here? So what I would like to estimate or to look at is the empirical eigenvalue distribution. So this is something that we will study in more detail during the TD, eigenvalue distribution. So I want to compute the density of eigenvalues, and for that I will define. Okay, I introduce this notation, which is the way that mathematician would denote this thing here. So I have this 1 over n. I have this delta of lambda I. Now what it means is that if you compute mu n of lambda, this is just a sum of Dirac delta function. Okay, so these are just delta functions, and this is called the empirical eigenvalue distribution. Okay, so you would like to understand the structure of this guy here in the limit of large n. So the first thing that you would like to compute is the average. So again, the lambda i's are random and they are distributed according to that Boltzmann weight here. Okay, and you would like to compute this density. So this is something that we will do later. There are various ways to do this computation. We will present one approach in the tutorial. Let me just give you the result and comment a little bit. Again, we will derive this result in a few, right after. So the first thing that you would like to compute is the average value of this quantity. Okay, so expectation value. Okay, so you would like to look at this expectation value of mu n of lambda, and of course, what you can imagine is that it's clear that for a given realization of the lambda i's, this is just the sum of delta function. So it's a very irregular function. In fact, it's not a function; it's a distribution, of course. But it turns out that in the large n limit, this actually becomes a nice smooth function when you both average over the lambda i's and then eventually take the limit n goes to infinity. Well, you obtain a very nice and simple function, which is known under the name of the Vignor semicircle. Okay, so let me call it SC of lambda. So that converges to a nice function of lambda independently of n, and this is just this quantity which has a support of order 1, and this is just this Vignor semicircle, which probably you have already seen before. And this, of course, is only true for lambda between -2 and +2. Okay, so this is this famous Vignor semicircle between -2 and +2. And outside of this region here, the density is just 0. Okay. Now, there is actually more to say about that, and we will encounter that also a bit later in the tutorial, is that, and that also connects to what you have heard several times during this lecture here, is that it turns out that this mu n of lambda here, you see, for each values of lambda, I might think of it as a random variable. Okay, because the lambda i's are random, so I just take the lambda i's and I construct some functions, some distributions out of these lambda i's, and that's a random variable. Now it turns out that, and here what I have computed is the average value of this random variable. Now it turns out that this quantity, this random variable, is self-averaging, in the sense that when n goes to infinity, this quantity here converges to its mean value. Okay, at least if you are not too close from the boundaries here. Okay, so if you take a lambda which is far enough from -2 or +2, then this mu n of lambda is self-averaging, and you can approximate essentially mu n of lambda by its expectation value. Okay, so that means that so for lambda in the, say, let's call it -2 +2, okay, and not too close. I will maybe comment on that in a minute. Not too close to -2 or +2. It turns out that this mu n is self-averaging. Okay, that means that mu n of lambda, indeed, when n goes to infinity, it's actually okay. So the fluctuations, if you want, of this function are extremely small as n goes to infinity. Okay, so that's a very nice result, very simple, and of course, as many times when we study or obtain such simple results for a relatively simple model, you should keep in mind that we study the GOE. GOE is also very similar. It will also be given by the Vignor semicircle, but of course it's a quite simplified model, okay? And it's quite important to wonder how universal are these results. So that's what I want to discuss briefly. It turns out that these questions of universality have actually attracted a lot of attentions in math literature during the last 25 years, and there has been a lot of progress. Again, usually these universality behaviors and results are more the business of mathematicians, because they really need tools that physicists probably don't have to really prove rigorously universality and universal behaviors. But it turns out that the Vignor semicircle, so I want to discuss this universality in two different contexts. First, in the context of Vignor matrices. Okay, so you remember Vignor matrices. This is the case where you have basically independent entries, but they are not necessarily Gaussians. Okay. Now it turns out that the Vignor semicircle, so this result here, so mu SC holds. So you will get the same density provided for distribution of the entries which have such that basically the first and second moments are well defined. So say, since here I was discussing one specific case, so Mij is equal to 0, so I need the first moment to be 0, and then this quantity here, the variance is just sigma squared, say, finite. And in principle, the third, the fourth moment can be anything, including infinite. But provided I have this statement here, these properties, then eventually in the large n limit, I will end up with the Vignor semicircle. Okay, so it's a kind of central limit theorem, if you want, for random matrices. There are actually extensions of these results where you might have some dependence on I and j, and under some circumstances, you can again show that the Vignor semicircle holds. There are also some cases where the MIJs might be slightly correlated, but not too much, where you would expect again to recover the Vignor semicircle. But that just to give you the flavor that the Vignor semicircle is extremely robust for such Vignor matrices. I just gave in the notes, I mean, you can have a look. I mean, I gave the reference to the paper by Laszlo Erdős on the archive. This is not the Erdős that you know, it's another Erdős, but very famous in this context of universality proofs. So that's for Vignor matrices. Now, what about invariant ensembles? Well, up to now, I didn't discuss so much invariant ensembles, except for the Gaussians, say the GOE and GUE. But maybe that's a good place to briefly discuss other invariant ensembles. So I gave the GOE, but in fact, more generally, how do they look like? Well, it's not very complicated to show that the typical way, or I mean, the shape of the distribution in this family of random matrices has this shape. Okay, so this is just, again, you will get the van der Monde. I mean, this term, lambda I minus lambda j to the beta. Beta equals 1 for GOE, beta equals 2 for GUE. But then, instead of having the Gaussian, you might have something more complicated, which could be, for instance, of that type. Okay, so that's the general probability measure that you would get for rotationally invariant ensemble. So the lambda I squared is just the the Gaussian ensemble, GOE, GUE. But more generally, you could have a V of lambda. Okay, so that means that if I interpret this in terms of the Dysons of the Coulomb gas or log gas, instead of having a quadratic potential, I may have other types of potentials. And the question that you want to ask is what happens to the density if V is not quadratic? Well, it turns out that in this case, if you change V instead of being quadratic, take something else, but sufficiently confining, you will again find a density which has a finite support, but in general, you will find a distribution which is quite different from the Vignor semicircle. Okay, so from that perspective, in this context, the Vignor semicircle is less universal for this rotationally invariant, but what you can show is that is still that, let me make this statement. So if lambda divided by log of lambda, roughly, so if it's more confining than a log, okay, so if V grows at infinity faster than log of lambda, then what you can show is that the density, the empirical density, mu n of lambda, will converge to a nice distribution, and it will have a finite support. But in general, different from the Vignor semicircle. However, and if I have time, I will discuss this a little bit more in detail, but however, it turns out that there are still some features which are similar to the Vignor semicircle. So that means that typically here you can obtain values. I mean, okay, if suppose that V of lambda is symmetric, then mu n of lambda might have crazy, it can have all sorts of crazy feature. Okay. Now the point is that you will have a finite support, say lambda minus, lambda plus, and exactly as in the Vignor semicircle case, you see there is one feature which is interesting here is that the density vanishes as a square root. Okay, this you can immediately see on the explicit expression. Now it turns out that except if you fine tune your potential V of lambda, I will not discuss this in detail because this is quite subtle, but generically the density will again behave as lambda plus minus lambda square root. And this means that a consequence of that is that for all these models, it turns out that if you look at what happens close to the edge, so close to the right edge, well, basically the statistics are very quite universal and very similar from one model to another. And this is due to the fact that this density has this square root singularity at the edge, and that's something that people have realized relatively recently. Okay, so maybe I still have a few minutes, so I would like to end up precisely by discussing the local statistics. So the moral of that is that, okay, Vignor matrices essentially they all behave in a relatively similar ways. Even on a global scale, so if I look at the global scale, that should be given again by the Vignor semicircle, which is quite robust. On the other hand, these rotationally invariant ensembles, or you might again think of it as Coulomb gas problems. If you change V of lambda, then globally the statistics will be different because in particular the density will not be given by the Vignor semicircle. But nevertheless, if you look at local statistics, they may become again universal. Okay, so that's something that I want to discuss with. Sorry. So I will end up with that because these questions have actually drawn a lot of attention during these last years. Also because they have many implications in physics. That's what I want to discuss. So what do I have in mind by discussing local statistics is the following. That's the last part. It will be very quick. Let's look again at this. Sorry. I have this support, which is of order between -2 and +2. And inside this support here, I have n particles, okay? I have n particles because I know that the density is concentrated on this. So the idea is that since I have n particles in this segment, which is of order 1, well, if I look at what happens near the center, what you will see is that the density is very much, I mean, doesn't vary very rapidly. And in particular, if I look at the distance, interparticle distance, well, it's easy to estimate because you see, I have n particles in an interval which is of order 1. So typically, the interparticle distance is of order 1 over n. Okay, so that means that if I am not too far from the edges, what happens is that in this regime, which is close to the center, which we call usually the bulk, that is called the bulk of the spectrum. In the bulk of the spectrum, well, if you look at for instance, the interparticle spacing, so the typical scale of lambda I plus 1 minus lambda I, so delta lambda, I've not ordered them, but if I look at the delta of lambda, so the gap, if you want, between two successive eigenvalues, well, again, because of this very simple argument, this is just given by 1 over n. And something that you can ask, for instance, is what is the distribution of this gap between two eigenvalues? And this is something that people, I mean, in the early 50s, in fact, 50s, 60s, 70s, people have studied a lot in the context of nuclear theory that I mentioned in the beginning, because they had access to a lot of data, and they could really compare and measure the gap that they would observe in real experiments on heavy nuclei, and compare this to the predictions that you would get from random matrices. And this is precisely what is called the Vignor surmise that was the subject of the homework, if you had a chance to look at it. But the Vignor surmise precisely measures or gives the distribution of the gap inside the bulk. Okay, so the distribution of the gap distribution in this regime gap distribution is given by Vignor surmise. Okay, so that's what was the subject of the homework. So that's called the bulk. Now, as you can imagine, what happens when you get close to the edge is much more subtle, because of course, as you go far away from the center of the trap, or the center of the V of lambda squared, you see, you would expect that the density gets smaller and smaller, and eventually the density will completely vanish. So that indicates that, in fact, the interparticle distance close to the edge is actually different from what it is in the center. So, in other words, what I'm trying to say is that in these models, it turns out that there are two separate regimes of scales. One, which is the bulk, where the interparticle distance is of order, typically of order 1 over n. But if you go to the edge here, and if you look at what happens between the gap between these two particles, it turns out that the spacing is much wider than 1 over n. And if you are here, instead of having 1 over n, you have something which is much more complicated, or different, which is 1 over n to the power 2/3. And that defines the edge of the spectrum. And at the edge, things are much more complicated, and the interparticle distance delta of lambda is given now by something else, which is 1 over n to the power 2/3. And the statistics at the edge here turns out to be very, very different, and they are loosely described by what is now known under the name of the Tracy fluctuations, from the name of the two people who have discovered this regime. And it turns out that close to this edge, the fluctuations of the eigenvalues, which are close to the edge, are extremely rich, and they are connected to a wide variety of problems, in particular these directed polymers in random media. But this is also nicely related to these problems of stochastic growth models, like the Cardar-Parisi-Zhang universality class, for instance. And the study of this edge here has actually generated a huge amount of work during these last years, because it turns out to be connected to many other interesting problems. So I would not have time to elaborate more on that, but I could give you some references if you are interested. But I think that already covers enough of what I wanted to tell you about the random matrices. So during the tutorial, basically we will see a way to compute this Vignor semicircle for the GOE case, using a rather, I mean, not fully rigorous, but quite precise way to do that. And we will also discuss universality, by the way. Okay, so I think I will stop here. So the tutorial will take place as usual on the on Zoom, and we will use this group as we have done the other days. So let's meet there maybe in I don't know, say in 10 minutes, maybe at yeah, let's meet at 4:05 or something like that. Of course, I will be happy to take questions if you have any. And otherwise, we will just meet in a few minutes.